my name is Kohosuda from Osaka University, a professor in Osaka University, and now we are sitting next to Rolf. I mean, he is now a professor in the Osaka University as well. And this year, in some sense, the Osaka University is organizing this the Shanghai lecture to some extent. It is our great honor. And actually, I got my PhD from Kyoto University, and I'm working for robotics for more than 20, how many years? 24 or 5 years. And I had an experience to stay in Zurich, 1998 to 1999 with Rolf Pfeiffer. And since then I study about basically the embodiment. And now these 10 years we are studying about the structure of the muscular skeletal system, which we human and also the biological system has. And to what extent that kind of structure is contributing to the intelligent behavior. So that's a very brief, short introduction to myself. And not yet Fabio is coming back, but maybe I can start, huh? Right?
Yeah.
Okay, so maybe I gradually start my talk. The title is the Muscular Skeletal Bionic Robots, and we'll see what bionic means. And first of all, let's see the video clip from the DARPA Robotics Challenge. This is a very big, the fund. I mean, the DARPA is a very big, the army staff, and they are providing a lot of, they provided a lot of the fund to boost up the humanoid tasks, for example, to open a door in the disaster place. And this is actually the challenge this last year. In this video, we see the robot who won the game from the name of the company, the Shaft, from Japan. And you see how the robot opened the door. Okay, please, Nathan, will you please start the video one? Because the movement of the robot is really slow, I speed up at 8 times. So it's a bit winding up motion, but you will see how it opened the door. Okay, thank you very much. And then please see the next video in which our muscular skeletal type robot opens the door. Will you please start the next video, please? Yeah, the quote is not good. Yeah.
Is it time?
Yes, it's real time. Okay. And you could see that the second video, in the second video, the muscular skeletal robot moves very naturally to open the door, right? And actually the trick is we just apply random input to each muscle. So basically the motion is not really programmed, but the body naturally realizes that kind of door opening task. Whereas in the first video, the robot is really hardcore programmed to open the door and see the speed. And you can easily understand what kind of function the muscular skeletal system is providing. Okay, that's the essence of my talk. So if the robot, I mean the muscular skeletal system is well designed, it will be more adaptive and it needs less control. This is the take-home message for you now. Okay, so of course, generally speaking, designing dynamics for adaptive behavior is a kind of open program. You can design whatever you want to realize the adaptive behavior. But because it is a completely open program, it is really difficult to come up with very clever and nice design. So maybe the very good start is to mimic humans or animals and to try to, reproduce the structure, the muscular skeletal structure as much as possible so that you can understand what kind of functions that the system has. And this is what we call bionic robots. In this sense, we want to reproduce to some extent the biological system by the robots. And following this philosophy, we developed several kinds of bionic robots. And these are actually some of, not all of, some of our robots. So we have developed more than maybe 30, 40 robots. And each robot basically try to mimic, to some extent, the structure of the human. And I will pick 3 examples up from these robots in this presentation. And basically, I have to say that the promise of us is that the muscular skeletal structure is the key for adaptive behavior. Okay? And I want to say, for the first place, we cannot use the real muscle, the living muscle. So instead, we are using artificial muscle, what we call, and this is built from rubber tube and also the plastic sleeve. And if we put the plastic sleeve on the rubber tube, then when we put the air to the rubber tube, it will glow, and simultaneously it will generate force along the longitudinal way. This is what they call McKibben type artificial pneumatic muscle, and we basically utilize this muscle for every robot. And in this presentation, as I told, we are going to pick 3 examples. One example is the dynamic walking and balancing, and also the hopping. And finally, we talk about we are looking at the dexterous manipulation. Okay, first of all, I will start about the simple walking on a flat plane. Does not need too much computation. To prove this fact, we developed several types of robots, and these are basically the history of our robots. So we start developing this kind of bipedal robot from 2003 until now, so more than 10 years now. And I will show 2 robots out of this list. And the first robot is what we call Mutt BB. This is a bipedal robot, and actually this is a constraint in the 2D. So we can call it 2D walker. And additional to say, it is driven by pneumatic muscles, as I already introduced, and also the structure of the muscle is almost similar to the human. And the amazing thing is that normally, if you build up a humanoid robot, you have to put many kinds of sensors. For example, the gyro sensor and the angle sensor, and also the accelerometer to sense the attitude, so on and so. And also, sometimes they put a vision as well, and touch sensor. So many sensors, basically. But for walking, this robot only needs 2 touch sensors and nothing else. for example, we don't need any gyro sensor. Just 2 switches make it work. And we'll see how it works. Okay, Nathan, will you please start the video 3 now? So the robot is moving, the working on the moving plane. And if the robot touch to the ground, then the other leg start to spin. That's the only control program to the robot. So the programming is really simple, but it works forever. And it can keep the balance. And also, you can see that the working is relatively adaptive, right? They are stable, I must say. And as I explained, the robot has a similar structure as a human, so I a little bit explain about how is the structure of the human. We human not only has the, we human has a joint, and the joint is driven by 2 muscles, basically. So one is pushing, then it will go this way, and the other is pulling, then it go this way. Okay, so the one joint is controlled by 2 muscles basically. But the medical observation say that we human has 9 muscles to control the lower leg. So not only the muscles which we call antagonistic. Antagonistic means the one joint is controlled by the 2 muscles in the opposite direction. But to control the 3 joint, we only need 6 muscles. But the lower leg has the 9 muscles, means that 3 muscles additional. And what 3 muscles doing is that the muscle is going not only from this way to this way, but from this way to this way. Means that the one muscle is controlling 2 joints simultaneously, which we call biarticular muscle. And they say that that kind of biarticular muscle is really contributing to coordination between the joint. Okay, so if you want to coordinate the motions of joints, you don't need program, but you need the biarticular muscles instead. That kind of idea is applied to the robot, and as a result, the robot can walk very stably on the flat plane. And we actually extend the idea not only the biped, but also the whole body humanoid, which we call Mutt BB. And this robot is has basically whole body, not only the legs, but also the torso and the arm. And because this robot is driven by the pneumatic artificial muscles, it's completely compliant. So if you apply the force to the robot, it's, it can be powerless. I mean, if you have a robot like this, the pepper, it is driven by the electric motors. So it's very stiff because the robot don't have electricity now, but so it's really soft. But normally, if you apply the electricity, it's really stiff. But this Mutt BB, because it is driven by pneumatic actuators, pneumatic artificial muscles, it is completely compliant, and you will see in the video. Will you please start the video 4 now? So there are several joints, but applying the force, you can easily move it like this. So for this kind of robot, standing still is a very big challenge. You see, if the robot is really stiff, just power off, make it standing up. That's it. But for the robot which is really compliant, then you have to apply compliance to move to stand the body up. So the next video will show how we can realize the standing up motion of the robot. Will you please start the video 5 now? So the robot merely standing up, but it's really compliant, so you can apply the force, and you can see how the robot reacts to the external force. You can hear the noise, and the noise means that it's open and close the valve, so that the robot will provide air to the one of the muscle, or exhaust the air out of the muscle.
So was that real time?
Yes, everything. I mean, my video is everything there in real time. Because you have to understand the dynamics, right? Okay. So this is a very good example to understand dynamics of the robot now. Okay. And by extending this kind of idea to not only to the humanoid but also to the quadruped, we also realize the quadruped robot walking, what we call new part, because
Can I make have a quick question?
Yes.
So I mean, dynamics. The term dynamics is used in different ways in different areas.
Yeah. Right.
Could you perhaps briefly explain, just very briefly, what the way in which you are using the term dynamics?
Thank you very much for your suggestion. In my presentation, the dynamics means, for example, mass, or spring, or damper. So basically the property which consists of our body. And for example, if you have mass in your arm, you can swing really naturally, right? This is the exploiting dynamics stuff. Okay, this is the sense of the dynamics in this presentation. Thank you for clarifying this. And now we are moving to the next slide, and we are now applying the same idea, mimic as much as possible the structure of the biological system by the robot. And this is what we call new part, which is basically a big cat, feline type robot. And actually this video is on YouTube, so you can just put the keyword new part to find out this video. Okay, will you please start the video 6, Nathan? This is again real time. And actually the motion is pre-programmed, but because the robot is really compliant, it looks like complying against the movement of the floor. So it's really biological system-like, and some of the tendon is realized by the lower tube, as you see. Yeah, this is again 2D. Now we are conducting the steps on 3D that not yet presented, I must say. Okay, thank you very much. And the fundamental message is that for the quadruped, I must say, the robot only has 4 touch sensors again, not gyro sensor, no angle sensors, but 4 touch sensors to each tips of the legs. And also the pneumatic actuators, and if you are really special about the controlling stuffs, then controlling pneumatics is a kind of a last thing that you want to do. I mean, to control the pneumatic is really, really difficult because of the fluid dynamics. But because we properly design the body, we don't have to take care of that kind of property, but we just apply a kind of pre-programmed sequence. So, but the compliance will deal with the change of the environment. So we don't need too much computation. Because of that, we normally use very simple, very small CPU. For example, the walking robot, we use the only 16-bit disk tip, which is driven by the 60 megahertz. Whereas, if you control this kind of robot, you need a large computer power. Okay, so this is a very important message of my presentation. If you properly design the robot, I use the muscular skeletal system, for example, you can reduce the computation, but still the robot will move properly. Now we moving to the next topic about the hopping. Not only walking, but we also study about the hopping, and we also develop several types of hopping robot. And out of this, I want to pick one robot, which we call Kukaku, means that the air leg in Japanese. This robot is monopod with biarticular muscles, as I explained. Basically, the structure of the muscle is the same as the robot I showed in the first place. The robot walking on a flat plane. And applying the same idea, to use the muscles to coordinate between joints, then we can easily, again, to move it hop. Okay, will you please start the video 7 now? Okay, maybe once more. It's a quick video. You see that the movement is really natural, right? And again, the robot has only one sensor, a touch sensor, so that it can sense the timing of the touch. And then after the robot senses a touch, the robot will pursue to realize the motion by a fixed sequence of the muscles. So the program is relatively simple, but you can see that the hopping is relatively stable. We think that that kind of stability is brought by the structure of the muscular skeletal system. Okay, so by imitating more about the human body, then the required control hopping becomes more and more simpler. And again, the message is, if the body is well designed, simple control enable hopping. Okay? And because the robot only hops, we want to make it not only hop but walk. So we put two of them into one robot and make it bipedal robot like this. And try to realize the hopping by the robot. Okay, will you please start the video 8 now? So there are several tricks, but basically the idea is the same. We just apply the reflex-based control. After the touch sensed, then fixed sequence will execute it. That's all. So that kind of, the muscular skeletal structure is really effective to the hopping, is not only applied to the monopods, but also the biped. Okay? And of course, this robot is since the robot is biped, it can walk. So we also did an experiment to make it walk, and unfortunately, this video maybe I didn't upload to Nathan, so maybe we cannot see this. But the very interesting thing is that the robot can jump up that kind of high, and the same robot can walk on a flat plane. So it can realize multimodal, I must say, 2 modes of locomotion by the same hardware. That's a very interesting point. I mean, this is a very good demonstration to change of the adaptively change the situation. Okay. So finally, we go to the last example. For human-like body, it is easy to achieve human tasks. Again, not too much computation. To prove this, we develop the upper torso, the arm. And this robot is basically, again, mimic the fundamental structure of the human body. And it has, as far as I remember, more than 40 muscles on the robot. So it has a lot of muscles on the robot. And also it has a hand. And we put the 2 cameras on the top of it, but we still don't have implemented too much program on it. But anyway, as I explained, the structure is try to mimic the human, and if you observe the human body, we learn a lot of interesting features of the human. For example, the wrist. The wrist is a kind of a semisphere, and it can rotate like this, and rotate like this, but not like this. Okay? If you want to rotate this along this axis, then this 2 bones will twist it like this. Okay? So this, if you realize by the robot, then you put 3 motors here. So the robot move like this, move like this, and move like this. Okay? So basically the movement is a bit different in between. And as I explained, these 2 bones also utilized for this twisted motion. So in this robot, we also mimic the structure of the human by these 2 bones. And these are basically the muscular skeletal structure of the robot. So you can see, what you can see is that many muscles on the robot. Okay? If you know something about the anatomy, then you will realize which muscle is which. But here you don't have to understand this. But you see that many muscles, and also the structure of the muscle is really interesting. For example, to twist it like this, we have 2 muscles here and here. I actually forget the name of the ulum and whatever it means. There are several names, but there are 2 muscles to twist the hand, twist the wrist like this. Okay. And because we design very human-like, it is applicable to the human-like task. For example, the task to open the door. This is actually the same video as I showed second, but maybe it's nice to see it again. So will you please start the video 2 again? Now you can see that what is going on in this video. So because the robot has the same structure as a human, even if you apply random excitation to the muscles, the robot will move really human-like because it has the same structure as a human. Our environment is basically designed for our body. For example, the doorknob is designed for our body. So if the doorknob is placed on the top of the door or the bottom of the door, it's really hard to twist it, right? But if the knob is in front of you, then it's really easy to open. It is a very good example to explain the environment is designed for your body. And because a robot has the same structure as a human, for the robot, it is also easy to open the door. That's the trick of this experiment. And we also try to mimic the shoulder blade, because the shoulder blade is the one of the most complicated, complex structure of the human. So it's a very good trial to mimic the motion of the shoulder blade. And now, currently, we realize this kind of motion. Will you please start the video 9 now, Nathan? So the student is trying to move the arm, and you see the movement looks really natural. Maybe as if you move the other humans the arm. And the robot has the and also during the movement, the robot learns the movement, the motion of the arm, so that it can reproduce movement like this. There are many technical details, but all you have to see now is that the movement is really natural, looks like a human. Okay? Okay, the conclusion of this experiment is that if we properly design the robot body, it is easy for the robot to deal with the human tasks. So through these 3 examples, we see how adaptive these bionic robots are. And the essence, the take-home message is, again, designing dynamics for adaptive behavior is basically open problem, but mimicking humans or animals is a very good start to understand the adaptive behavior. And this is what we call bionic robots. Okay, this is the end of my talk. Thank you very much.
Thank you. Well, I think we have many questions, so who is the first?
I have a question for you. I would like you to detail a little bit more the type of control, which is the difference with the classic methods and with your methods.
Yes, in the classical way, normally you control divided into small pieces. For example, the joint level control, right? If you use the electric motors, then you control each joint by each control, and build up a whole body, whole movement of the body. But in this case, because the muscle is basically distributed throughout the body, so you cannot really control each joint. So you have to change drastically the concept how you control the robot. And but so that means that to develop the control will be a disaster. But on the other hand, the robot is properly designed. The dynamics. Then you can reiterate the dynamics. Then control would be simpler. You have to control each joint very precisely. That's the essence of the control in this.
Yeah, so you have basically to run a very specific and precise model of all the muscle that you have and the interaction between them. So I think it should be much more complex. Yeah, okay. Thank you. Can you hear me now?
Yes.
Yes. So I mean, you have to run basically a model in which you take into account all the interaction between your muscles. If I'm right.
No. Well, we don't use any model. Well, it's quite difficult to define what model is. I mean, because the robot is kind of a model of our body. Okay, so our muscular skeletal system will react naturally. For example, when you are pushed like this, and if you want to model it, of course you can use the equations. But also, if you build up a muscular skeletal robot, you can realize the similar motion. This is also a model of your movement, right? But for realizing the muscular skeletal robot, the only knowledge you need is how you can connect the bone to the muscles, but not for example, the dynamic equation of motion or so and so. Okay, so you don't need the very precise equations to describe the system, but just construct the robot by the artificial muscle and bones. That will be a very good model of your dynamics. Maybe that might be the answer to your question, right?
Yeah. Okay, thank you.
I am interested in the power consumption of this method respect the traditional method. So did you carry the test about this?
Okay, that's actually a good question. And for the locomotion, you see the biped walking, right? And the biped walking is basically utilize the mass of the leg. So if you want to swing the leg like this, you need the mass to swing it forward. Okay, but if you control precisely the motion of the leg in each time, then you need a much computational power and also the much energy, electricity to make it feedback. So for the case of the bipedal walking, the efficiency is relatively good comparing to the traditional type of electrically driven robots. But for the jumping robot or also the arm, because the robot has many muscles, and actually the fluid dynamic is not really efficient comparing to the electric motors. They are not actually really energy efficient, I must say. But basically you can utilize the compliance, the muscles, natural compliance of the muscles. So if you efficiently utilize the compliance, then it will be a bit efficient. But I don't know. We haven't tested yet.
Hello, thank you for your talk. I have two questions basically. The first one is, did you think or did you investigate the role of ligaments so that introduce some compliance also in the joints? Because in our case, in our body, joints are not exactly like rigid joints. I mean, they have also compliance in the other degrees of freedom, the ones that are not free to move. And the second one is, how did you tune the parameters for controlling these robots? Is there a learning phase or is it just done by hand, by chance? Thank you.
Okay, that's also a very interesting question. I mean, of course, if you build up a robot to mimic all of the ligaments and all of the muscles from the very start, then it will be really complicated. And you cannot really figure out what kind of control you have to, think. but we basically have the opposite way to, start from very simple idea. For example, the bipedal robot, we start from what they call passive dynamic walker, which has only 2 legs and no motors. And then we put the muscles on it and try to investigate the function of the muscles, and to put additional muscles on it, try to investigate the function of the additional muscles, and so on and so. Maybe we have to some extent, piling up the knowledge, how we can add the muscles to the robot. That's the way how we design the robot. Maybe that's maybe the answer to the first question. And second question, of course, because the system is really complicated, the control strategy, to figure out the control strategy is very, very difficult. But as I told, if you start from very simple example to the complicated, then you can utilize the idea you already had in a simple case, for example. And also, we also look up some of the medical books telling that for this kind, for example, the walking, they need this kind of the sequence of the excitation of the muscles by measuring the humans, right? So to some extent, we can utilize such kind of idea when to excite which muscle, and we can develop a control strategy for the robot. But the parameters, I must say, the parameters we have to tune by hand. And finally, one of the students will take care how much you put when to which muscle, and so on. So it's a kind of time consuming, but of course it depends on the dynamics of the robot. So yeah, finally it will be programmed by the hand.
So other questions?
Yeah, Fabio.
No, I was actually asking if someone else had a question. So actually you finished with answering to this question saying you have to do it by hand, right? In which direction you think we could try to develop some more, let's say, more structured method? Because actually you said before that designing dynamics for adaptive behavior is an open problem. But from your standpoint, in which direction we should look to try to solve the problem of designing the dynamics? I understand it's a big question, so a short question and then maybe a short answer to this question.
Okay. Let's see the door opening task. In the door opening task, we apply only the random input to open the door, right? You remember. And then you don't need any program at all. But applying the random door, the robot will happen to open the door, means that by memorizing that kind of sequence, the robot will learn how to open the door, for example. So if you design the body properly, then maybe the learning will be simpler. So we can maybe get rid of the effort for programming.
Okay, thank you. So if there are not other questions, I think we can thank Ko for his really inspiring talk as usual. And so, thank you.